In this lecture, you'll learn why we have the spanning tree protocol. And to understand why we need to have it, I need to first start off with a review of Ethernet path selection. So we've got our example network topology on the left-hand side here again. And our layer 2 Ethernet path selection is controlled by the switch's MAC address tables. So let's see how those are built and how it works. In this example I'm going to cover here, PC1 wants to send traffic to the 10.10.10.2 IP address on R1. And in this example, I'll cover what would happen if we didn't have spanning tree, and then you'll understand why we need to have it. So PC1, it hasn't spoken to R1 before, so it sends an ARP request for 10.10.10.2. That goes out with a source MAC of 1.1.1, the MAC address on PC1, and a destination MAC of f.f.f because it's broadcast traffic. So PC1 sends that out and it will hit switch access 3. Access 3 learns that MAC address 1.1.1 is available via interface fast0/1 because it saw that as the source MAC address in the incoming frame. Any subsequent traffic that is going to 1.1.1 that hits switch access 3 will be forwarded out port fast0/1. Switch access 3 floods that broadcast ARP request out all ports apart from the one it was received on. So it goes out interfaces fast0/24 and fast0/21. Switched CD1 learns that MAC address 1.1.1 is available via interface fast0/24 when that ARP request comes in. And when it comes into switch CD2, it learns that the MAC address 1.1.1 is available via its interface fast0/21. So you can see that the MAC address tables are getting built on the switches here as traffic hits them. Any subsequent traffic for 1.1.1 that hits either CD1 or CD2 will be forwarded out those relevant ports. Switch CD1 floods the broadcast traffic out all ports apart from the one that it was received on there, and the traffic will then reach R1. It also reaches CD2 and access 4. R1 will respond to the ARP request. CD1 learns that MAC address 2.2.2 on R1 is available via interface gig 0/1 from that ARP reply. So any subsequent traffic for 2.2.2 will be forwarded out that port. So switch CD1 now knows the best ports to send traffic out for both R1 and for PC1. Switch CD1 already knows to forward that ARP request for 1.1.1 out towards PC1 on interface fast0/24. It comes into switch access 3 and it learns that MAC address 2.2.2, the source address in the ARP reply from R1, is available via interface fast0/24. So any subsequent traffic for 2.2.2 that hits switch access 3 will be forwarded out port fast0/24. And we now have end-to-end path selection in both directions between PC1 and R1 going through the switches access 3 and CD1, and the switches know which port to send the traffic out of. But there's a problem here, and to understand it, let's go back to the start to when the ARP request from PC1 first came in to the switch access 3. So switch access 3 received that ARP request from PC1 and it floods the broadcast traffic out all ports apart from the one it was received on. This is if we don't have spanning tree. So that includes port fast0/24 facing CD1 and the port facing CD2 as well. Switch CD1 receives the ARP request from access 3 and it floods the broadcast traffic out all ports apart from the one it was received on. That includes going out its interface gig 0/2 towards CD2. CD2 does the same thing. It floods the broadcast traffic out all ports apart from the one it was received on, and that includes port fast 0/21, which is facing back towards switch access 3 again. The traffic comes into access 3, and access 3 sends the traffic back to CD1 again, which will then send it back to CD2, which will then send it back to access 3, and so on and so on. So we now have a loop running clockwise between the access 3, CD1 and CD2 switches. Whenever we've got broadcast traffic, it's going to keep looping between the three of them. But it doesn't end there. The broadcast traffic was also forwarded out interface fast 0/21 by access 3 when the ARP request came in. So we also have a loop running counterclockwise between access 3, CD2 and CD1. So you can see the ARP request comes in, access 3 sends it to CD2, CD2 sends it to CD1, CD1 to access 3 back to CD2, and so on. We have loops running in both directions, both clockwise and counterclockwise between access 3, CD1 and CD2. Still, it doesn't stop there, because the broadcast traffic was also forwarded out interface fast 0/21 by switch CD1. So we also have a loop running counterclockwise between CD1, access 4 and CD2. And the broadcast traffic was also flooded out interface fast 0/24 by CD2, so we also have a loop running clockwise between CD2, access 4 and CD1. So just like we have two loops running clockwise and counterclockwise between access 3, CD1 and CD2, we have the same thing, two loops running clockwise and counterclockwise between access 4, CD1 and CD2. So we've got 4 loops running through the network here. And the layer 2 Ethernet header does not have a TTL time to live field to stop the looping traffic like our layer 3 IP header does. So on a layer 2 network, if you get traffic looping, it will loop forever. There's nothing to stop that happening. But if you do get a loop happening, the way you can stop it is by physically going and unplugging a cable. And there's going to be more broadcast traffic on our network than just that single ARP request from PC1 going to R1. There's going to be loads of other broadcast traffic as well, like other ARP requests, DHCP requests, etc. And if we do have loops on the network with all that broadcast traffic going around, we're going to get a broadcast storm. The network will crash because the amount of looping broadcast traffic will quickly overwhelm the switch's CPU and bandwidth. So if you do get a broadcast storm on your network, it's devastating for the network. It will stop the network from working. So a broadcast storm obviously must be avoided at all costs. And the way that we do avoid it is by using the spanning tree protocol. It's used to prevent any layer 2 loops. It does that by detecting any potential loops and blocking ports to prevent them. In our example network, you can see on the diagram on the left, if you look at the different links, you'll notice there's a couple that are highlighted in red rather than in green. Port fast 0/21 on switch access 3 is highlighted in red, so it's been blocked to prevent the loops both clockwise and counterclockwise that were running between CD1, CD2 and access 3. We also had that other loop between access 4, CD1 and CD2 as well, so on that side, port fast 0/24 on access 4 switch has been blocked. So spanning tree, it will detect potential loops and it will block a port to break the loop. But if you look at it now, before, from access 3, if both uplinks, fast 0/24 and fast 0/21 were up, if we weren't blocking any ports, then we would be able to send traffic upstream to both CD1 and CD2 via the fast 0/24 and the fast 0/21 interfaces. Let's say that those are 1 gig interfaces. We would have had 2 gigs worth of uplink bandwidth. But because one of those ports has been shut down, we're only using half of our available physically connected uplink bandwidth. We've only got 1 gig's worth of uplink connectivity rather than 2 gig. So spanning tree, it actually shuts down physically cabled interfaces. It reduces the amount of bandwidth that you have available. So it's an evil, but it's a necessary evil, because if we got a broadcast storm, the network wouldn't work at all. So that would obviously be a far worse scenario. Spanning tree automates failover as well as performing loop prevention. So if an access layer switches uplink to CD1 fails, you see in the example here on both access 3 and access 4, those switches, their available uplink is the one facing towards CD1. The core distribution layer 2 CD2 switch, both the uplinks from our access layer switches to it are blocking right now to prevent the loops. But if switch CD1 goes down, or the links to CD1 go down, spanning tree will detect that and it will fail the uplinks over to using CD2 instead. But we already covered one of the bad things about spanning tree, which is it limits the amount of bandwidth you have by shutting down interfaces that are actually physically cabled. Another bad thing about spanning tree is it typically has a slow convergence time. It can actually take up to 50 seconds to converge. So spanning tree, it's got some bad things about it, but it's absolutely necessary in networks because it's far more important to ensure that we don't have any layer 2 loops. But we would like to minimize the use of spanning tree if we can. I'll get into some methods we can use to do that at the end of the next section. In this section, as a network engineer, you have to understand spanning tree. So the rest of this section will go through how spanning tree works, how to configure it, and by the end of that, you'll also understand how to troubleshoot it as well. Thanks for watching. If you want to get hands-on practice with Cisco networks for free, then you can download my 400-page CCNA Lab Guide, which you can see above my head right now. Also, check out the video about my CCNA course. It's the highest rated course online. Thanks.